Okay, today we're going to look at solving systems of equations. We're going to start off with two equations, two unknowns, x and y. Don't know either one. Basically, there are three possibilities for two lines on a graph. The two lines can cross. The two lines can be parallel, or they could actually be the same line. Solving a system of two equations and two unknowns means finding out whether they do cross, are parallel, or coincidence. If they cross, there will be one point that can solve both equations simultaneously. In other words, that one point, that one xy value, will solve both of them. If they are parallel, then there won't be any solutions to your problem. It'll be the empty set, and if they are coincident, then every point on one line will of course work on the other line because they are the same line, in fact, even if they look different to begin with this. There are several ways to do this. One of those ways, of course, is by graphing. Graphing, however, is probably the least effective one because it depends on how detailed your graph is for actually locating that point if they do cross, especially if it is not, say, right on whole numbers of x and y. We're going to look here at some algebraic methods for doing that. One of those is called the elimination method. Basically, you figure out how to eliminate one of the variables and therefore end up with one equation with one variable that you can then solve. The other possibility is substitution. So first here we have an elimination, combining the equations to eliminate one of the variables. So note that if we take the second equation and multiply everybody by -3, we end up with the first equation has a plus 3y, the second equation has a -3y. So then when we add those two equations together, we have eliminated the y variable and we're left with just -2x equals -2. We go ahead and solve. We'll get x equals 1, and then plugging that into either of the equations, we find out that in fact y equals 4. And if we were to plug the solution 1, 2 into either equation, we would find out that it would be a solution for both. So for instance, up here, 4 and then 3 times 2, 6, that would give us 10. And in the second one, we would have, let's see, 2 times 1, that's 2. And that would give us an answer there as well. So that's the idea behind that. Now, because again, 2 times 1 would be 2, and then plus 2 there would be our 4. Now, another way we can do it is called substitution. Substitution is where we rearrange one of the equations so that it can be written as a single variable equals the rest of the equation. We then take that and substitute it into the other equation. So here we rewrote this one as y equals -2x plus 4. Take the -2x plus 4, substitute it in for the y in the other equation. Now we have again one equation and one variable. We can solve for our x and get our final solution when we plug it back in for y. Generally speaking, we don't necessarily want to do the substitution if that's going to give us a problem with a bunch of fractions in it. However, either one can work. Now, extending beyond that, suppose we go to the situation in which we don't have just two equations and two unknowns, but we're going to have three equations and three unknowns, x, y, and z. This would represent a straight line in space, not on a plane, but in the dimensions of a room. The solution to the three equations with three variables will be an ordered triplet, x, y, and z. And again, that has to solve all three equations. There are several different possibilities here. You could have all three lines intersect at one point. You could have two of them parallel, but not the third. You could have all of them going in directions in which they're not actually parallel, but they don't actually intersect either, because you now have that third dimension to have to deal with. We have a type of elimination method for solving these types of problems. I recommend the very first step is that you label the three equations. It really doesn't matter which one you want to call 1, 2, and 3, but you label them so that you can kind of keep them straight. And then in pairs, you set them up so that you can eliminate a variable. The key, however, is that you want to eliminate the same variable in two different pairs of equations. So here we have taken equations 1 and 2, and notice that we have a plus y and a minus y, and so when we add these two together, since those are already opposites, we can get 3x plus 2z equals 9. And then a different pair of the three equations, here equations 2 and 3, we can take the equation 2, which we have doubled, and then we have equation 3. Now it is the, again, y values that are canceling out, and this will leave us with two equations in which we only have x and z in the two results. Then we can go back to say a substitution method, because this has a single z by it. Z equals 5x minus 2. Substitute that into the other one. Hey, now we've got an x. Then we can come back and solve for z, and then we can go into any of the three original equations to find out what our y is. I usually pick the one in which the coefficients are the smallest, and then we have our solution. Again, the key is combining two different pairs to eliminate the same variable. All right, so that's the basis of what's in the section. Let's look at some examples now. We'll start off with a couple of problems in which we only have two equations and two unknowns, and then we'll look at some examples with three of them. So, in this first one, I do note that I have just a single y in this one, so I could do a substitution. So I'm going to rearrange that one to become y equals 3x subtract 5. Again, the sign of the negative 3x switches when I put it on the other side. Still have the negative 5. I am now going to substitute that into the other equation. So 2x subtract 3, and then in here I'm putting my 3x subtract 5, and then that equals negative 6. So I have one equation and one unknown. Now I can distribute 2x subtract 9x plus 15 equals the negative 6. Go ahead and combine like terms. Negative 7x equals negative 21, and so I'm left with x equals 3. Now that I have that, substitute it back into the other equation. So y is going to equal 3 times the x, which I just got to be 3. Subtract 5, that's going to be 9 minus 5, which is 4, and so my answer is going to be 3, 4. And again, notice how I've written the answer here. It is actually a point on a graph where these two lines would cross. Now, I could have also done this doing the elimination method. So, for example, I could have taken the second equation and multiplied it times 3. So let's go ahead and look at that. We're going to do 3 times the negative 3x plus y equals negative 5. So that would give us negative 9x plus 3y equals negative 15. Now, the other equation, which I haven't done anything to, that is 2x subtract 3y equals negative 6. Note how I have a plus 3 and a minus 3. I think of that as now they're matching. They're opposite in sign, but they're the same value. I can go ahead and add the two together. I have my negative 7x. Over here I have the negative 21. And notice that I'm right back to x equals 3. And then I can go back into either equation to find out the other part. Negative 3 times, again, the 3 that I just found, plus y equals negative 5. So, rearranging, that ends up with y equals 4, and so I have the same answer there, 3, 4. So, first off, by doing the elimination, and then, or excuse me, this was doing substitution. And then this was doing elimination. So two different ways to solve the problem. All right, let's look at a second example. Notice in this particular case that I have coefficients in front of everybody, so if I wanted to use substitution, I would end up with some fractions because, you know, if I was doing the x's, I would have to divide everybody by 3 here and everybody by 2 here. If I was doing the y's, I would have to divide by 5 or divide by 3 to get the y all by itself. So instead, we're going to do the elimination method. And again, the goal is make one of the variables be the same, or what I call matching, one positive, one negative. So what I'm going to do is I'm going to take the top one here, and I'm going to multiply everybody by 2. So that would give me 6x subtract 10y equals negative 4. In the second one, I'm going to take everybody and multiply it by negative 3. So that would give me negative 6x plus 9y. Notice it's plus 9y because this is negative 3 times negative 3, and then equals negative 3. And so now, because I have a plus 6 and a minus 6x, when I add these two together, I get rid of the x's. I end up with negative y equals negative 7, and therefore y equals 7. And then, now that I have that, I can come back to 2x, subtract 3. I'm going to put in that 7 equals 1. And so now I have 2x equals 22, and therefore x equals 11. And so my answer is 11.7. Now in this particular case, I picked getting rid of the x's. It does not matter. I could have picked getting rid of the y's. So for example, I could have taken the first one, 3x minus 5y equals negative 2, and multiplied that by 3. And then the second one, 2x subtract 3y equals 1. Multiplied that by -5. So this one would have given me 9x subtract 15y equals -6. The other one would have given me let's see, -10x, -5 times 2, plus 15y equals -5. Add these two together, I have a -x equals a -11, therefore x equals 11. Plug that back in. 2 times the 11, subtract the 3y equals 1, leads to -3y equals -21, so y is 7, and I'm still with 11, 7. So in the first case I got rid of the x's, in the second case I got rid of the y's. What is preferred? Bottom line, whichever one you see first, or whichever one is easier for you to see. I like to pick ones usually that have the smaller numbers, so I would have picked the x one normally first, because 3 and 2 it's easier to get to 6. 5 and 3 it's not really hard to get to 15, but depending on the situation, the bigger the numbers are, the easier a chance to accidentally make a mistake. So here are our ways of solving two equations and two unknowns. Alright, so now we're going to look at solving 3 equations and 3 unknowns, x, y, and z. And as I said, really first important step, go ahead and label your 3 equations. I usually just do it the way they're listed, and then I'm going to be looking for trying to get rid of the same variable. I note in this particular example I have all 2x's and the third one is -2x, so it's a pretty simple thing to just get rid of the x's. I could go after the y's, because all I would have to do is make this one doubled, and then it would be plus 4y, and then all the y's would be something easy to do, but I'm going to go ahead and start with the x's. So basically adding 1 and 3, so let's go ahead and do that. 2x subtract 4y plus c equals 1. -2x plus 2y plus 4z equals 2. Put those two together, the x's are gone, and I have -2y plus 5z equals 3. Okay, now I have to have a different pair, and so in this case I'm going to do adding 2 and 3. So adding 2 and 3, again the goal is to get rid of the same variable in both cases. So 2x plus 4y subtract 6z equals 2, -2x plus 2y plus 4z equals 2. Again, the x's are gone. Now I have 6y subtract 2z equals 4. So the x has been eliminated. Alright, so if I look at the two equations I have left, -2y plus 5z equals 3, and 6y minus 2z equals 4. One of the things I note is I have a negative 2 and a plus 6 here, so if I take this one and go times 3, then I'll end up with a negative 6y. This one has a plus 6y, and I can get rid of the y's. So let's go ahead and do that. Tripling the top one, I end up with negative 6y plus 15z equals 9. The bottom one, just rewrite 6y, subtract 2z equals 4. And so 13z equals 13. Z is 1. Okay, now that I have that, let's go back to this equation to find out my z. So, or find out my y, excuse me. So 6y minus 2 times the 1 for the z. Actually, that's a 2, sorry. 2 times the 1 is 4. So that's going to give me 6y equals 6. And so y equals 1. And now that I have that, let's go back to, say, the top equation. 2x subtract 4 plus the z. Both of those guys were 1s. Doesn't have to be that way, it just happens to be in this case. And so I'm going to end up with 2x equals 4, or x equals 2, and therefore my answer is 2, 1, 1. And so we have solved 3 equations and 3 unknowns. It is obviously more work than in the 2 equation cases, but really it's just doing the elimination method some extra times. The real key is coming back here, figuring out which variable with 2 different pairs of equations to do that can go ahead and get rid of the same variable. Alright, here's another one. Again, this is my 1, 2, 3. And so, you know, I start to look at them to see what letter I can get rid of. You know, here, 9, well, 3 times 3 would give me 9. I could do that 9. And then I like, oh wait, this is 3, this is 3. In fact, if I take this one, and I go times 3, then I'm going to have 9x plus 3y minus 6z equals 21. And I don't change this one at all. Let's just write it out. Negative 9x subtract 3y plus 6z equals 5. And if I add these two together, well, the x's are gone, the y's are gone, the z's are gone, and I'm left with 0 equals 26, which of course is not true, and therefore there will be no solution. And in fact, what has happened is these 2 lines are parallel. If, on the other hand, this had come out with, like, say, 0 equals 0 or 26 equals 26, something that would have been true, but all the variables would have been gone, then that would have meant they were the same line in that case, instead of 2 different lines. Even though they might have looked different to begin with, they were in fact the same line. But in this case, since 2 of the lines are parallel, there's no one point that will go that will be valid solution for all three lines, and so the answer is we have no solution. All right, now an interesting use of three equations and three unknowns can be looking at solving for the equation of a parabola where we know it goes through several points and we want to find that equation. So if we look at our basic equation here for a parabola, y equals ax squared plus bx plus c. That's the standard form for a quadratic. And it goes through these points in which x, y's for each one of those. Now you might at first blush think, well, wait a minute, there's not three variables, but the actual variables we're looking for are the a, the b, and the c. So let's go ahead and rewrite these. So the first thing I'm going to do is I'm going to switch it so it's ax squared plus bx plus c equals y. And then we're going to write out variations of this based on those 3 points that this parabola passes through. So in the first case, we would have a times 2 squared plus b times 2 plus c has to equal 4. In the second case, we would have a times -1 squared plus b times -1 plus c has to equal 1. And in the third case, we have a times -2 squared plus b times -2 plus c equals 5. Okay, so this would become 4a plus 2b plus c equals 4. The next one would become a minus b plus c equals 1. And then 4a subtract 2b plus c equals 5. And so here now we have our three equations and three unknowns. So I'm going to basically say that this is equation 1, equation 2, and equation 3. And so first we're going to do, basically, since they all have the same c, let's get rid of c first. And so I'm going to do equation 1 subtract equation 2. Now if you want, you can always think of this as I'm multiplying equation 2 times -1 and then adding it to equation 1, or excuse me, multiplying equation 2 times -1 and then adding it to equation 1. And so we'll just go ahead and write those out. 4a plus 2b plus c equals 4. Now everybody in this one gets the negative, so subtract a plus b subtract c equals -1. And so the c's are gone, and I'm left with 3a plus 3b equals 3. And then in the second case, I'm going to take equation 1 and subtract equation 3. And again, subtract can just be multiply by -1 and then add. So here I'm going to take, again, 4a plus 2b plus c equals 4. I'm not changing that equation at all. And then, let's see, it'd be -4a plus 2b negative c equals -5. the A's are gone, I end up with 4B, and the C's are gone, and I end up with -1. Now this is okay, because I can now solve for the B. B is going to be -1/4. The key is I set these things up so that I got rid of the C's in both cases. But now that I have that, I can come back into another equation. So for instance, if I take this one right here, where I have 3a plus 3b equals 3, and then I'm going to put in that -1/4, so 3a plus 3 times the -1/4 equals 3. So 3a will equal 15/4. Did skip a couple of steps there. I have to go to fourths here, so that will be 12. 3/4, it'll be negative, but then when I put it on the other side, it becomes positive. So 12/4 plus 3/4 gives me 15/4. Divide both sides by the 3 here. Now my A is 5/4. And now that I have that, I can say go back to problem 2. Problem 2 had A minus B plus C equals 1. I could have gone back to any of them, but I chose that one just because I don't have any coefficients to worry about. So I'm going to have 5/4 and then the -1/4 plus C equals 1. And since I am subtracting a negative, that becomes an add. So 6/4 plus C equals 1. And therefore C is going to equal 2/4, actually -2/4, which is a -1/2. And so my answer will be 5/4, -1/4, -1/2. Now, that would be as if it was a point of the ABC, but what we were really looking for, again, this is not the answer. It's always important to be aware of what was the actual question. The actual question was to find the ABC of the equation. So instead, the answer will be, and I'm just going to do it this way, 5/4 x squared subtract 1/4 x subtract 1/2. There is the actual answer. It's always important when you're solving algebraic equations to recognize that in some cases they represent other things, and so that your answer has to actually go and answer the question, not simply, oh, I solved the problem and therefore I'm done. And so the actual answer is y equals 5/4 x squared subtract 1/4 x subtract 1/2. And there you have section 5.1.